A, don't say anything silly, or B, say something silly. Take your pick. All right. I have a feeling something silly will get said at some point.
Time to begin the journey into outer space.
Space. Yeah.
Calculate this all into a cookie.
I don't have a cookie. I have no cookie for which to calculate this all.
Your acceptance of this universe entails you are accepting cookies. Oh, that's a website.
Oh. Cookies.
Cookies, right? Cookies, yes.
You got it.
Not those cookies.
Right, other cookies. Yes, the good kind. Let's see. Let's get it slightly in here. Up, could it be?
There is a V.
There is a V. Yes. Because we're living in the universe. Where did I start? Verse. Oh, that's right. Because
What is that?
V never gets tired of the same verse.
Did you see what was on Google? What was that?
I don't know. Something funky. Oh, this is the problem. Dr. K is logged in. All right. Dr. H.
Who's Dr. K?
I know, yeah.
Really deep.
On the last day of class,
Let's see.
you realize there's no difference.
Sign out. How do you get away? Go on, go away.
Hertha Marks Ayrton was a British engineer, mathematician, physicist, and inventor.
Oh, this is actually.
Known for her work she was awarded the Hughes Medal by the Royal Society for her work on electric arcs and ripples in sand and water.
Oh, all right then.
Cool.
Okay.
So yes, it was turbulence. Very good. Good observation.
See, that's what I saw. I was like, that looks like physics.
No, I don't know. Dave quiz me. Go away.
Those look like stable sinks.
Did you?
All right.
How's Wednesday afternoon?
For the exam.
For the exam.
We set it like 7:30 p.m.
Oh, instead of, yeah, I'll get that.
Right. Yeah.
So,
That's
when in
fine.
the afternoon? Should we figure out like 2?
Yeah, we should pick a time. Yeah, I guess we'll.
So,
The normal start is 1:30.
1:30.
I'm okay with 1:30.
Yeah, 1:30. All right. It's a date. Very good. Nice.
What a great date.
Oh, I know. Yes, awesome. It's stellar. It's galactic. It's something. It's.
So, I
It was
was
actually challenging.
combining a couple of exams. Is it still going to be a 3-hour test?
Yeah.
It's gonna be on everything, right?
It's going to be on what would have been chapter 2.
Why did
No,
you-
what would have been exam? What would have been
I
exam?
love picking stuff and stuff on that.
Whoops. What would have been stuff on exam 2 plus the last stuff. So it's not
So it's over everything we haven't been tested on.
correct. That's the short version. Yes. Courses.
GR.
GR. Yeah.
That'd be great. Did you see Brandy's Facebook post from Florence?
Yeah.
So what about their normal?
Duomo,
Yes.
Duomo.
Yep. Yes. And then meanwhile, Kaylee got the SciShow job.
Did she
She
really?
did, as a matter of fact. Yes.
That's awesome.
Yep.
You said 1:30, right?
1:30. That's right. Yes. Great. Okay. So this presentation is mostly legit now. Is this stuff legit? What's today's date? 19th?
28.
28th. Okay,
Say the
that's not,
19th.
that's not right then, so maybe it's a one. I want something, no, where is it? I know I'm not find it. Is it somewhere else? Listed events? We interrupt this
You
program.
can sort it by last modified.
Oh, here, no, 2:12 p.m. I was looking at the wrong thing. Okay, yeah, 2:12 p.m. That's fine. No, that's better. Okay, right. Okay, that makes it believable. Well, you can watch that crash course astronomy stuff later if you want to, but that's not what we're going to do. So, I'm going to leave it to you to read the notes about continuing this business of how does Z depend on distance, because we've only got one class left. So what's the relationship between, I'm sorry, how does flux correlate with Z in an expanding universe, which is equivalent to saying how does magnitude correlate with Z and one of the homework problems has you basically show where a plot like this comes from. And so the big picture is that how apparent magnitude correlates with z versus absolute magnitude. Notice how the distance modulus correlates with z depends on the expansion history of the universe. And so one can plot curves, like you'll do in the homework, for various expansion histories. What would the relationship between distance modulus, apparent magnitude minus absolute magnitude, and z be? And the supernova data followed best a curve which corresponds to an accelerating universe. In other words, one that has dark energy in it, one that has a significant contribution. The most, excuse me, I made a joke up. The most significant contribution to the energy densities from the dark energy. And this is showing that in more detail here. And so I'll let you illuminate yourself, so to speak, by doing that homework problem and looking through the notes for the rest of that. Because I want to say something about the cosmic microwave background radiation and how we use it to determine that universe is flat, and how we can also use it to determine how much dark matter versus not dark matter there is, and from the flatness infer then how much dark energy there is. So in other words, it's not just supernova observations which tell us those things. So first of all, the cosmic microwave background radiation, I think you all know, one way or another, is literally microwave radiation that's coming to us from every direction, and it's leftover radiation from the Big Bang. The radiation that we're seeing was not directly created right at the Big Bang, but in other words, the universe was very hot when it was young, and so it was ionized. But as the universe expanded, the wavelengths of the radiation that was filling it increased, and so therefore the universe cooled as it expanded, because photons lose energy as the universe expands. And so eventually the universe cooled down enough for hydrogen atoms to form for the first time. In other words, for protons and electrons to get together and make hydrogen atoms for the very first time. And since it was the very first time that ever happened, that combination is naturally called recombination, which makes no sense whatsoever, but whatever, we're stuck with it. Normally you call electrons uniting with protons to form hydrogen atoms. You usually call that recombination, and they just kept the name. For the very first recombination ever, it's called the era of recombination, except it should be combination because they've never been combined before. So as we'll detail in the next couple of slides, the idea is that before recombination, the universe was opaque. The mean free paths of photons were not very large. They couldn't travel very far. But after recombination, the universe was, in terms of ordinary matter, stuff that interacts significantly with light, it was neutral hydrogen. And neutral hydrogen is pretty close to transparent, is what it comes down to, because most photons are not able to be absorbed by neutral hydrogen. And so, as a result, the universe became transparent at recombination. It was about 380,000 or so years old. We can calculate when that happened. That's when the temperature of the universe cooled down to about 3,000 Kelvin, enough for recombination to occur. And ever since then, the leftover radiation from the hot early universe has been free to travel through the universe, but meanwhile the universe has been expanding. And so that leftover radiation, which has an almost perfect black body spectrum, has been getting longer and longer wavelengths and therefore shifting to lower and lower temperature. So this is the cosmic background radiation spectrum as measured by the COBE spacecraft, the Cosmic Background Explorer spacecraft. It's also been measured by WMAP and by Planck, but this is COBE from back in, I think it was the late 80s, when it flew originally. Its principal investigator, George Smoot, got on the cover of People magazine because it really made quite a a splash when its results, not this, but its results, it was the first low-resolution maps of the anisotrophies of the cosmic microwave background radiation. They were dubbed the ripples of creation, and it made even like, popular level news and so forth. So he was on the cover of People magazine, like in rollerblades or something. So, yes?
Anisotropy.
Not being the same in every direction. Yeah, not being the same in every direction. If you have perfect black body radiation, it's absolutely isotropic. It's the same in every direction. The CBR, or CMB, it goes by cosmic microwave background. CMBR, cosmic microwave background radiation. CBR, cosmic background radiation. Nobody's ever agreed on what it should be called. So these are all CMB, I think, is probably the most common. Anyway, here is the cosmic microwave background radiation's spectrum as measured by COBE. That's the squares. And the smooth curve is the best fit black body spectrum. I'd say it's a pretty good fit. It's really, really close to being a perfect black body spectrum. And it corresponds to a temperature of about 2.7 Kelvin. And that's not because that was the temperature of the universe when the radiation was released by recombination. It's because the scale factor back when the radiation was released was about 1/1100. And so as a result, the radiation is now at about 1100 times the wavelength or 1100 times lower temperature than at the time of recombination. So in other words, take the temperature now and multiply by about 1100. That corresponds to the temperature when recombination occurred. We actually do the calculation the other way. You can calculate when what temperature recombination would occur at. You measure the temperature today, and you use that to infer what the scale factor was at the time of recombination. So a few billion years ago, the cosmic microwave background would have been at a warmer temperature because the scale factor wasn't as big as it is now. It's less than 1 then, not as big compared to when the radiation was released.
Before we move on from that thought.
Yep.
What's up with those units on the side?
It's ergs per second per square centimeter per steradian per centimeter. Is that what you're saying?
Yeah.
Right. So in other words,
Per inverse centimeter.
per inverse centimeter. I'd have to think of, per inverse. So remember that. So it's specific intensity, okay, per unit wavelength interval is the idea.
What is
So.
the erg?
Oh, it's the CGS unit of energy. So in other words, instead of a kilogram meter per second squared, it's a gram centimeter per second squared.
Okay.
And then you got steradians, right? So it's because it is specific intensity per unit wavelength interval. So that then you multiply by the wavelength interval, and you would get the energy in that wavelength interval. So, okay. So here's a little cartoon. Before recombination, free protons, free electrons everywhere. Photons can't get very far because the free electrons scatter. Just like in the interior of a star, the primary source of opacity is electron scattering, and that was true in the early universe as well before recombination because of the fact that the electrons were free. On the other hand, recombination happens, protons combine with electrons, and then the photons are free to travel. The universe has essentially become transparent. So the idea is, remember that when we look into the distance, we are looking into the past, right? If you see a galaxy that's 2 million light years away, you're seeing as it was 2 million years ago, and so forth. So as we look farther and farther out into space, we're looking back farther and farther into the past. If you look back, if you look far enough into the distance, far enough into deep space, you eventually are seeing the time of recombination. You eventually see this. You eventually see a surface surrounding us that corresponds to the time of recombination. We're getting light from it today that was emitted by that surface at the time of recombination. And if you look any further back than that, you'd be looking to times before recombination when the universe was opaque. So that's what this is representing. Turns out this is not to scale. The surface of last scattering, we call it, or in other words, the surface where the photons in the early universe were last scattered before recombination occurs so that they can then travel freely through the universe. It's about 14,000 megaparsecs away. That's on the order of 45 billion light years away. Again, that's bigger than the distance that light could travel in the age of the universe. Why? The universe has been expanding, right? So that's the present proper distance. It's not how far away it was from us when the photons were started sending or started heading our way. Its present proper distance is about 45 billion light years from us. So that surface, that sphere that's about 45 billion light years away from us that is sending us photons from the time of recombination, when we look at the cosmic, when we look, quote unquote, when we image the cosmic background microwave background radiation, what we're seeing is microwaves from that so-called surface of last scattering. That's what Planck and WMAP and Cody before it are imaging when they look at the cosmic background radiation. We can't see beyond that, so that surface acts kind of like a photosphere at a redshift of about 1100. And so it's not a zero thickness, but it's relatively thin because recombination happened pretty quickly. And so after recombination, the mean free path is very long. Before recombination, it's rather short. So pretty much what happens is we're seeing photons that are now free to stream towards us, having never been able to stream freely before recombination. So that's what we're seeing when we see the cosmic background radiation. That's what WMAP and Planck are looking at. They're looking at the so-called surface of last scattering.
How do they do that?
They literally have microwave antennas that measure carefully the radiation coming from different directions.
So they just know that all radiation below like a certain frequency.
They have to, so they're looking relatively near the peak of the cosmic background radiation, corresponding to a temperature of around 2.7 Kelvin, which works out to, I think, about a millimeter wavelength. So, but they do have to carefully subtract other sources. Like, in other words, the raw images show the plane of the Milky Way, for example, because there's certainly stuff in the Milky Way that is emitting at those wavelengths as well. So they have to very carefully subtract out nearby sources. It's an arduous, very, very detailed process in order to image just the cosmic microwave background radiation. So that is not a trivial thing, as a matter of fact. WMAP is at the L2 Lagrangian point in the Earth-Sun system. I think Planck is too, as a matter of fact. So here's just a cute little thing. Greetings from L2. Hey. Was that? Yeah, I know, you might as well, huh? Right? Just multiplies the fun. It's definitely not a minimum of fun. Okay, anyway, so these are the results. This is a color-coded map of the cosmic microwave background anisotropy, not the same in every direction. They also have to subtract out this overall motion of our galaxy relative to the frame in which the cosmic expansion is uniform surroundings. In other words, our galaxy has peculiar motion relative to the expansion of the universe. Galaxies not only are dragged apart by the expansion of space, they're moving through space, quote unquote. And so there's this overall blue shift in one direction of the sky and red shift in the other due to our motion relative to the frame in which the cosmic microwave background is most nearly isotropic. That had to be subtracted off as well. But that's actually the easy part. It's much harder to subtract all those other sources like galactic radiation in that regime and so forth. So this is a map of the temperature corresponding to different directions on the celestial sphere. So you've probably seen maps before where you show the entire Earth on kind of an oval. And so on those maps, be like, here's North America, here's South America, here's Europe, here's Asia, here's Australia, here's Antarctica, right? Same projection is being made here to map the celestial sphere surrounding us onto an oval shape like that. So this is the entire sky, and here it is just projected onto the surface of a sphere where you can imagine us being in the center of this and looking outwards. And in fact, I have seen like beach balls with this image on it. Yeah, that's pretty awesome. And you can get yourself one of those. But in any case, it's color coded so that, because they're terrible physicists apparently, red is warmer and blue is cooler. Of course, we know it's really the other way around. But people think of red as a hot color and blue as a cool color, so they color code it for whatever reason, making the red hotter and blue cooler. Just to make the public like it better, I guess. In any case, so if the cosmic microwave background were a true black body spectrum, there'd be no structure whatsoever in this. It would be exactly the same temperature in every direction. But in fact, there are anisotropies on the order of 1 part in 10,000 from one direction to another.
Isn't it 100,000?
I think it's a few parts in 100,000, if I'm not mistaken. So,
100,000 to the degree.
yeah, I think it's a few hundred thousandths of a degree, if I'm not mistaken, is what it comes down to. So there's very
Oh, it says
tiny.
it right there.
Does it say? What do they say? Where?
100,000.
Also, anisotropies are only
Some hundred thousandths of a degree. So it's a few hundred thousandths of a degree compared to. So 2.725 Kelvin is the overall temperature, but there's small fluctuations out in like the fifth point after the decimal point, fifth place after the decimal point in those temperatures. And those slight fluctuations tell us all kinds of interesting things about the universe. And what those fluctuations are caused by is sound waves in the early universe. Sound waves that were propagating in the plasma of the early universe before recombination. Sound waves are associated with rarefaction and compression. When I'm talking to you, I'm sending sound waves your way, and so a given parcel of air, as the sound wave passes, gets rarefied and compressed as the sound wave goes by. It goes, so to speak. Sound waves in the early universe, which are at frequencies much lower than our ears could ever hear. Sound waves in the early universe were corresponding to rarefactions and compressions in the plasma of the early universe. And so when recombination happened, the photons started free streaming. What that means is when we look at that sphere around us corresponding to the time of recombination, we see these patterns because some regions were a little bit denser than average and some regions were a little bit less dense than average. And at the same time, some regions were a little bit hotter than average because they're compressed. Other regions were a little bit cooler than average. When a sound wave passes by, the compression of a sound wave does work on a parcel of gas. If you squeeze a parcel of gas, you do PEV work on it, and so it heats up. And when it expands, it does work on its surroundings and cools down. So these are hot and cool spots that are associated with rarefactions and compressions in sound waves in the early universe. And we're seeing a snapshot of them on our personal, if you will, surface of less scattering corresponding to recombination. Somebody in a different part of the universe would see a very similar pattern, but not the same, because the pattern of rarefactions and compressions they see will be corresponding to their surface of less scattering. But everybody will see something in general terms similar to this. And the question is, if we figure out what is the spectrum of sizes of spots of various angular sizes, what does that tell us about the early universe? universe? And the answer is a lot, and so we'll talk about that. So questions before we continue? Turn up the light. Kind of like it's. Okay. So, big picture, lowest level thing is you can imagine, you look at those spots and you figure out if you expand them in terms of spherical harmonics, and then you can get some sense of what is the angular scale, the size on the sky of the strongest fluctuations from isotropy. What is, in some sense, kind of an average spot size of those hot and cold blocks that we see on the surface of last scattering. The geometry of the universe affects how big the spots look to us. So here is just a quick reminder of the idea of course, this is two-dimensional analogies, but if you have a flat universe, then triangles add up to 180 degrees when you add the angles in them. The circumference of a circle, radius r, is 2 pi r. In a saddle-shaped space, then it turns out that the sum of the angles in a triangle is actually less than 180 degrees, where when you make a triangle, you have to make geodesics connecting the vertices of the triangle. That's the version of a line. That'll add up to less than 180 degrees on the surface of the saddle. And the circumference of a circle is greater than 2 pi times its radius, where the radius is the distance along the surface and the circumference is 2, the distance along the surface. And similarly on a sphere, angles add up on a triangle to more than 180 degrees, and that's easy to see. So for example, think of a sphere. You can easily, on the surface of the sphere, go to 2 points on the equator that are 90 degrees apart from one another, and then go up towards the North Pole. The angle of all three of those angles will then be 90 degrees, so they add up to 270 degrees, which is definitely bigger than 180 degrees. So angles on a triangle add up to more than 180 degrees on the surface of the sphere. Circumference is less than 2 pi times the radius, as we've already seen, and also area of a sphere is less than 4 pi r squared, where r is the radius of the sphere as measured in the curved space itself. So there's another effect, that's related to this effect, that, and again, this is the two-dimensional analogy, but it works in our three-dimensional universe too. Suppose our universe is a hypersphere. Let's look at the two-dimensional analogy. Here is some object whose which has some certain length, lambda, bad choice of symbol because it makes you think of wavelength. Here's some object with length lambda, some distance away. You let light rays come from either end of it straight to you. Light rays follow a straightest possible path, so they follow geodesics on the surface of the sphere. And because of the curvature of the sphere, the angle between the ends of the rod, as seen by us sitting at the North Pole, we like to think of ourselves as being at the North Pole of the sphere, is bigger than it would be in a flat space for a rod the same distance away. What that means is that the rod actually looks bigger than it would in a flat space if it were that same distance away. So the curvature of space has the effect of magnifying the apparent sizes of distant objects in a positively curved universe. In a saddle-shaped universe, it has exactly the opposite effect. The curvature of the paths of the light rays by the curvature of the universe has the effect of making things look smaller than they would the same distance away in a flat space. And I'm going to skip through here. These are from the textbook that I use in the cosmology class for non-science majors, and they like penguins. It's like, what is it, Halliday or Halliday? Yeah, right. So they probably were inspired by Halliday here. But I'll just use this this illustration here. So we can calculate from essentially fairly simple physics how big the strongest vibrations should be in the sound waves in the early universe. We can calculate how big they should be, and you can calculate that, based on that, that in a flat universe, the strongest peaks, the kind of, in some sense, the peaks that give the strongest contribution to the spectrum of fluctuations should be about 1 degree in angular size as seen from Earth. How big is the moon in angular size, do you know?
Half a degree.
About half a degree. So imagine looking at the cosmic microwave background radiation, because now you have magic microwave sensitive eyes. You would find that those fluctuations that I was showing you before on that map, they're about, the strongest contribution is from ones that are about twice the size of the full moon on the sky. And what we can do then to get information about the geometry of the universe is look at the actual cosmic microwave background radiation anisotropies and see how big are the hot and cold spots. If the universe is flat, the hot spots appear actual size. We'll find that the strongest contribution is from hot spots and cold spots that are about 1 degree across. But if the universe is spherical in shape, then what happens is that here's imagine the edges of a hot spot seen by us. Because of the curvature of space, notice that by the time the light reaches us, the angle between the photons is bigger than it would be if space were flat and I just drew a straight line from my eye to the edges of the hot spot. So in other words, a positively curved universe, the curvature of space has the effect of magnifying things. So it's like a makeup mirror. Objects in the mirror are further away than they appear because they look bigger than they should in the makeup mirror. So if the universe is closed, meaning that it's a sphere, it's finite in volume and so forth, hot spots appear larger than actual size. The hot spots would look bigger than a degree on the sky, the most prominent contribution. If the universe is open, which means saddle-shaped, you'd have the opposite effect. The curvature of space would make the angle smaller than it would be in a flat universe, and it would make the hot spots look smaller than actual size. I'm going to go into quite a bit more detail soon, but the short summary is that when we look at the actual cosmic microwave background anisotropies, what we see is consistent with the flat universe. That tells us that we're living in a flat universe. That's how we know that, is from looking at the power spectrum, strictly speaking, of the fluctuations in the cosmic microwave background spectrum. In other words, seeing their typical angular sizes is what it comes down to. That's the qualitative astronomy 111